between the hoop and the ground. And the main force here that I'm going to talk about later is the normal force that is exerting from the ground to the hoop. And F stands for the initial force that we give to the hoop, so it will start rolling on the ground. Now, if we give a coordinate system to the G, the center of mass, that will send an aggregate X, we can follow the theoretical work. So here, the hoop will have different kind of motions. Here we are investigating jumps, which will happen when the normal force is equal to 0. That is logically correct because when the hoop is jumping, there is no force that can be applied to the hoop by the ground. So the acceleration, vertical acceleration of point M will be equal to the mass point gravitational constant minus normal force. Because we don't have a normal force here, we can get this equation out of it. And if we consider the omega or the angular displacement will be around the center of gravity, it will be constant while the hoop is moving, while the hoop is jumping. So we can obtain a formula for the coordinate system x in y for the center of gravity. And it will start with the initial velocity, the time that's shown with t, and the alpha is the same as the theta, which is the angle between the mass and the stable equilibrium state. So we can obtain energy for the system. We can say that here, if we follow the equation, in the right part, on the right side, we can see the kinetic energy of the system, and in the left side is the potential energy. And if we follow this equation, it will give us one condition for the jump to occur in a minimal theta, which will give us this time of half of the theta will be greater or equal to the equation we have on the right side, and which has the main parameters of initial velocity, gravitational constant, and radius of the hoop. Now, to see if the experiment matches our theory, I have some different masses applied to the system and different hoops, which are plastic hoop, metal, and wooden one, and two different types of ceramic, so we can see how does the friction or less friction will affect this phenomenon. Now, as I said, the hoop is following a cycloid motion if we track only the hoop. But if we track the mass that is attached to it, it will follow a parabola shape. And the jump will happen when the parabola is outside the cycloid. And the theoretical framework, the GeoGebra simulation showed that too. Now, to see if our theory matches the experiment, this is the jump angle for the metal hoop, which is calculated with tracker 84.83 for the center of gravity. And it will start with the initial velocity, the time that's shown with t, and the alpha is the same as the theta, which is the angle between the mass and the stable equilibrium state. So we can obtain energy for the system. We can say that here, if we follow the equation, in the right part, on the right side, we can see the kinetic energy of the system, and in the left side is the potential energy. And if we follow this equation, it will give us one condition for the jump to occur in a minimal theta, which will give us this time of half of the theta will be greater or equal to the equation we have on the right side, and which has the main parameters of initial velocity, gravitational constant, and radius of the hoop. Now, to see if the experiment matches our theory, I have some different masses applied to the system and different hoops, which are plastic hoop, metal, and wooden one, and two different types of ceramic, so we can see how does the friction or less friction will affect this phenomenon. Now, as I said, the hoop is following a cycloid motion if we track only the hoop. But if we track the mass that is attached to it, it will follow a parabola shape. And the jump will happen when the parabola is outside the cycloid. And the theoretical framework, the GeoGebra simulation showed that too. Now, to see if our theory matches the experiment, this is the jump angle for the metal loop, which is calculated with tracker 84.83 degree. And if we use the equation we have in the theoretical framework, we can see the theta will be equal to 85. The same equation and the theory match will go for the plastic hoop and the wooden one. So basically it does match our theory with some error that was okay because of the problems we had with the problem we had in the experiment. Now we can see that how we can have a diagram that shows that what is the relation between the mass that is applied to the system with the angular displacement of the mass. So it will be a constant line. The angular displacement, as much as the angular displacement is increasing, the mass will stay the same. So, and another diagram shows a linear relationship between angular displacement and the initial velocity. So we can say that as much as the initial velocity is increasing, will the angular displacement or the theta of the mass will increase too. Now, to see where will the jumping motion happen, we have this ascending trend here for the relation between theta, the rotation angle, and the time diagram. We can see that the part that the diagram is increasing is where the jumping motion happens. And as I said, we will have a parabola shape if we follow the mass that is attached to the hoop, which can be seen in the left side. Now, to mention that I have the metal, plastic, and wooden hoop with different sizes and different masses applied to the system that they vary from 50 grams to 20 And one more time to mention that the hopping occurs, the parabola is outside of the cycloid. Now, if we want to see that how does the mass affect the hop size, we can say that when the for the metal hoop, as much as we are increasing the mass attached to the hoop, the hop size will increase too. The same thing happens for the plastic hoop and the wooden one. We can say the same ascending trend here. As much as we're increasing the mass, the hop size will increase too. Now, at the end, for the conclusion, so we saw that as much as we are increasing the mass applied to the system, the hop size will increase too, and we know that there will be a limit for that. So the limit is when the mass is we are increasing the mass, the inertia of the system is increasing too. So we will need